Okay, so now we're going to move on to coordinate geometry. This section begins with a lot of different definitions and short little methods which will be useful later on. Rather than break these up, I'm just going to give you them all to you at the beginning, and that gives us the option when we're doing later questions of which method we want to use. You can sometimes be quite flexible in which of the ideas you exploit later on. So none of these are really counterintuitive. They look like quite difficult formulas to learn, and you should know them well, but they come from quite natural ideas. So we'll begin with this one here. If you want to find the distance between 2 points, now this really exploits the usefulness of the way we do coordinates, what we call Cartesian coordinates or rectilinear coordinates. So looking at this here, we've been told that the length of a line joining two coordinates is given by the difference in the x-coordinate squared, add on to that the difference in the y-coordinate squared, and take the square root. Okay, square root means the positive one, so there is only one answer, the distance is a positive number. Now, you can actually be quite flexible with this. I mean, it doesn't actually matter which way around you take away the x-coordinates or which way around you take away the y-coordinates, because when you square it, positives and negatives don't matter. So make sure the x's are grouped together and the y's are grouped together, but within those brackets you don't need to be too fussy about it. So where does this idea come from? Well, I've called this distance L to begin with, and the reason I've called it that is so I can draw a diagram. So this diagram here marks on a point x1, y1, and a point x2, y2, and they're connected by this distance here which we're trying to find, which I've called L. Now, if I complete this into a right-angled triangle, we see the benefit of dealing with the kind of coordinates we do. If I look at the difference between their x-coordinates, that's a completely horizontal line. It's the difference between where this one is on the x-axis and where this one is on the x-axis. It's a distance like that. Now, this distance between the y-coordinates is the discrepancy between how high up this one is and how high up this one is. Now, those two distances make a right angle by the definition of x and y coordinates. So if you know what x2 minus x1 is and y2 minus y1 is, you can find L using Pythagoras. This is just a statement of Pythagoras. Another thing you might be asked to do if you've been given two coordinates is to find out where their midpoint is. And their midpoint is just the average of their x-coordinates and the average of their y-coordinates. If we go back to this diagram up here, and I'm trying to find out where is the halfway point between this point and this point, then I can simply say, well, this one is at a certain point in the x-coordinate, this one's at a certain point in the x-coordinate, so I'll place the midpoint halfway between them. So it's got an x-coordinate which is halfway between the other two x-coordinates. If I'm trying to find out how high up that point is, well, I look at where the y-coordinate of this point is, where the y-coordinate of that point is, and I go halfway in between, and that gives me the y-coordinates of that point. So the distance between 2 points is the discrepancy between the x's squared, the difference between the y squared, square root, and the midpoint between 2 points is the average of the x's and the average of the y's. This one here gives you just a number, usually a surd. This one here gives you a coordinate, so make sure it's written in brackets with a comma. Here we meet some familiar ideas, but with an extra piece of kind of detail to it. So parallel lines have the same gradient. They're going up at the same slope. They don't necessarily be kind of completely overlapping with each other, but they both have the same steepness. Okay? Perpendicular lines meet at a right angle, and here's an idea you might not be so familiar with. If these both meet at a right angle, then it's true that the gradient of one line and the gradient of the other line have a product which is -1. That means if you rearrange that, you can find one of their gradients by doing -1 over the other gradient. Now, trust me, it's an easy way of remembering it, is to learn that one gradient is the negative reciprocal of the other. Negative means make it a minus, reciprocal means flip it. So for instance, let's look at some numbers before we go any further. If I said, what line is perpendicular to that one? Well, it would have a gradient which is the negative reciprocal of that. So it would be the negative, and the reciprocal of that is 3 over 2. If I gave you the line -7 over 2 and said what gradient would be perpendicular to that one, I would make it negative, so it becomes positive, and I would make it its reciprocal. If I gave you something a bit simpler, like just 3, and said what's the negative reciprocal of 3, well, 3 is really 3 over 1, so it would become -1/3. So we can now write down gradients to make right angles with other gradients. The diagram is actually the one complication to this, which is if I gave you a gradient like this one here, the gradient of that line is 0 because it's completely flat. Okay, if you're going to write down y equals 0x plus 3, for instance, it has no gradient whatsoever. So actually the gradient of this one is infinite. I mean, you could sort of argue that, well, what do you times by 0 to get -1? Infinity sort of fits that role a little bit, but that's a special case. Okay, if you've got a horizontal line, then it's a vertical line which makes a right angle with it. And similarly, if you've got a vertical line which has an infinite gradient, then what is perpendicular to that is a horizontal line. Another familiar idea here is the idea of gradient. You've maybe learned gradient previously as rise over run. Well, that's still true. If you're trying to find the gradient of a line joining these 2 points here, then you would find out the difference in the y's and divide it by the difference in the x's. The crucial thing to be careful of here is to be consistent. Here I've done y2 take away y1 on the top, and x2 take away x1 on the bottom. You must keep that the same way. In fact, it wouldn't be wrong if you wanted instead to do y1 take away y2 on the top, but in that case you'd have to be doing x1 take away x2 on the bottom. You can see that there's just a factor of a minus which comes outside and cancels there. The idea is to be consistent on the top and the bottom line. You've seen that idea before. It shouldn't be too bad, hopefully. The main reason you might want to know the gradient is to be able to write out the equation of a line. Now, the equation of a straight line is y equals mx plus c. Okay? M is the gradient, which will be found by doing some kind of method like this, and the y-intercept has to be found by a different way. Either you're told what it is, or you can identify it from a graph, or you can find it by plugging in a value. If you've already worked out the gradient, then the y-intercept will be the only remaining mystery, so knowing any other point which is on the line would allow you to work out what c is. In a second, we're going to see a different way of writing out the equation of a line. One thing to notice is we said the Cartesian equation of a line. There are other ways of defining lines. Okay, there are lots of ways of describing where a line would be. It doesn't have to necessarily be a relationship between y and x coordinates. But this whole section of your course is focused on the idea of x and y coordinates and all the nice properties they have because of the right angles between the x and the y axis. And here is this other way of writing down the equation of a line. This requires you to know the gradient, just like before, and it requires you to know a point as well. Okay, we wrote down c before, but we knew c had to be found using a point. In this case, you're not writing down c, you're just plugging straight away in the point that you know. This y and this x here will stay in your equation, which is what you want, because the equation of a line does have a y and an x in it. The way this sort of works is like this. If I draw a line, and we're saying we know the gradient, and we're saying, well, hang on, we know a point as well. We know the point x1, y1. Then if you pick any other point in the line, I'm being very general here when I mark on this xy, it could be there, it could be there, it could be there, it could be anywhere. If you find out the gradient of the line connecting those two, which is that expression there, clearly it's exactly the same as the gradient of the line that you already know. This has its benefits sometimes, but in the following examples I will use the previous method. I will write down y equals mx plus c. I'll find m, just like you would for this one here, but then I will plug in a coordinate to find out what c is, and then go back to this version here. So let's look at our first example of actually doing something here. Some of these are quite routine. These examples are all jumbled up. You get easy followed by difficult, then another easy one. The challenge is to identify what method to use. So here, find the length of the line joining 2 points. You know exactly how to do this. It's Pythagoras in action. You find the difference between the, in this case I've done the difference between the x's, right, and then the difference between the y's, and I've squared them and taken the square root. You could have written the difference of the y's first and then the difference of the x's, because obviously the order you add doesn't matter. And again, as I said before, it wouldn't matter if you'd done 4 take away 10 in that one there, and even jumbled up in this case, and done this one the other way around. It doesn't matter which way around you do them, because when you square them, the pluses and the minuses don't matter. I've got an answer for this one here of the square root of 117. It's C1. I don't have a calculator in the exam, so I'd leave it like that. Another example here. It says points A and B, and you're given their coordinates. It says find by calculation which one of the points C, D, and E lies on the perpendicular bisector of AB. We've jumped straight in here to a very, very good question. This tests quite a lot. Okay, now there are various ways of doing this. I'll mention one other quite nice way of doing it in a second, but I'm going to just first of all try and find the equation of the perpendicular bisector. If I have an equation for it, then I can just plug these points in and see if they work. So let's find the equation of the perpendicular bisector of these 2 points. So be very clear you know what the perpendicular bisector is, but the name really gives it away. If I give you 2 points and I ask for the perpendicular bisector, then I'm saying, right, connect them up, find where the middle is. The perpendicular bisector goes to the middle because it bisects that line, and it is perpendicular, so it will make a right angle. So if I'm trying now to find out the equation of this line here, I know that it's perpendicular to the original line, and I know it passes through the midpoint. So I would like to know what the gradient of the original line is and what the midpoint of that line is. So that's what I've done. I've tried to find the midpoint of the original line. So the midpoint of those 2 coordinates there is averaging the x's, averaging the y's, so 3, 0. So my perpendicular bisector will pass through that point. I found out the gradient of the original line that I know, being very consistent with my x's and y's, and I've got minus a half. Now my perpendicular bisector must be perpendicular to that gradient. So I need a number which when you times it by that gives you minus 1. or in our terminology, we're going to find the the negative reciprocal even. So the minus disappears, you find the reciprocal of a half, which gives you 2. So my line here, this line I'm trying to write the equation for, has a gradient of 2 and passes through 3, 0. That's everything you need to write down the equation of that line. Straight away, y equals mx plus c becomes y equals 2x plus c, because I know what m is, I know what the gradient is. I need to find out what c is, so I need a point. I have a point. So I plug it in and I find out that c is minus 6, and that's the final mystery solved. Y is equal to 2x minus 6. I have the equation of my perpendicular bisector. Now to investigate these points here, I simply plug in the x and see if it does give me the y that it should. So when x is 3, on the perpendicular bisector, y is 0. Well, y is not 0 there, so that is not on the line. In fact, straight away, because the x-coordinate of 3 gives a y-coordinate of 0, we know this one's out as well. Checking the value of d, when x is 5, the perpendicular bisector has a y-coordinate of 4, so this is the one that works. Now, the other way you could have sort of done this is you could have set up a little equation in which you said, well, I know the gradient of this is minus a half, and then the difference between this point and the midpoint must have a product of minus 1 with the value minus a half. It's not particularly better. This has overdone it by finding the equation of the perpendicular bisector. That would be my preferred way of doing it. Okay, so this next example is talking about length, so it's going to be using our little Pythagorean formula. So you're given points O, A and B, you're given their coordinates, but A is unknown. It says as OA and OB are of equal length. Find the values of A. So I'm going to investigate the length of OA first of all. OA is the difference in the x-coordinates of O and A squared, the difference in the y-coordinate squared square root, so I end up getting this expression here. When I go to write down what OB is, OB all involves coordinates I know, and I get root 65. These two things here are supposed to be equal, so I've set them equal. Now be very careful in going from this line to this line. The square root means the positive answer to the question, what times by itself gives 65, or what times by itself gives a squared plus 49. I can just drop these square roots to get to this point here. There shouldn't be any plus minuses coming in at this point here. The plus minuses come now from rearranging this and getting that a squared equals 16. Okay, a squared equals 16 has two answers. So really this is a point that can't be made too often. If I give you a squared equals 16, you're solving that. It's very tempting to write that a equals the square root of 16 is plus or minus 4, which is simply not true, because the square root of 16 is just plus 4. If you're doing a question like this, the plus minus must come in straight away. Okay? You are recognizing that solving an equation with a squared gives two answers. Solving this equation with a squared in it gives you both of these answers. Okay? So, next example down here, it says the 4 points A, B, C and D, we know all of them, are the vertices of a quadrilateral. Show that AB is perpendicular to BD and that AB is parallel to CD. So if we've got perpendicular sides, we've got options here. It could be a square or it could be a rectangle. So being asked about perpendicular. Perpendicular is immediately making me think about the fact that the product of gradients is -1 or negative reciprocals. So let's look at AB first of all. So the gradient of AB, well, I'm working out here, and I found out the difference in the y's of the difference of the x's. I've been consistent. I've done B take away A on the top, and I've done B take away A on the bottom, and I've got the gradient of AB as a half. I go to work out the gradient of BD, and I've been consistent here as well. I've done the y-coordinate of D, take away the y-coordinate of B. I've done the x-coordinate of D, take away the x-coordinate of B. Be very careful that the formula requires you to do a takeaway. The fact there's a minus already there means that they have an interplay that gives you +2. So I've got the gradient of AB as a half, the gradient of BD is -2, and that means they're perpendicular because each one is the negative reciprocal of the other. Easier in this case to go back to the fundamental definition and say that the product of their gradients is -1. Okay, and it now says show that AB is parallel to CD. So I've already got the gradient of AB, so I'm hoping that CD has the same gradient. So let's look for the gradient of CD, and again, being consistent, I'm doing y-coordinate of D, take away y-coordinate of C, x-coordinate of D, take away x-coordinate of C. That gives me 1/2. 1/2 is exactly the same as I got before, so AB and CD are parallel because their gradients are the same. Next example, this is just a really nice, quick, easy question. So it says, find the coordinates of the midpoint of the straight line joining these 2 points. You're going to average the x-coordinates and average the y-coordinates, and you end up getting an answer of 3, 2. I mean, you can sort of see, if you think about how far it is to go from -2 to 8, the distance between those is 10. So if you go half the distance between those two, that's going 5. So 5 more than -2 is 3. Similar kind of idea for the y's. Being very careful here, I keep using the word average, but really what I mean here is the mean. There are other averages. I'm not talking about the mode or the median. So here we've got a slightly longer question. In this question, we're told 3 points, and there's a sort of unknown fourth point, and they're vertices of a parallelogram PQRS. What you can trust when you see PQRS is that that's the order of them. It must go PQRS. I mean, I've done that down here, PQRS. You don't really know where it starts in terms of whether it's going PQRS or it's going PQRS like that, but you do know that it follows round. You couldn't, for instance, go PQRS. Okay, this is a journey around the edge of a parallelogram. So, first of all, you're asked to find the coordinates of the midpoint of the diagonal PR. And that backs up what we said, P and R are not next to each other. So, the midpoint is done by averaging the x's, averaging the y's, and you get an answer of 1, 2. We then get on to part B, which says find the coordinates of S. So if you've got the other 3 coordinates of a parallelogram, where must that fourth coordinate be? There are a lot of ways of doing this. There are lots of different aspects of coordinate geometry you can use to solve this. This way here is quite long, but it's quite thorough because it practices most of the ideas we've met already. So I'm going to investigate some of the gradients going on here. So the gradient of PQ I found out to be -1, so the gradient of this is -1. The gradient of QR is 3. There's nothing significant about the relationship between these. They're not perpendicular. That would be possible because don't forget rectangles are special cases of parallelograms. So we do know that this is sort of a true parallelogram. It's not a rectangle because these two adjacent sides don't form a right angle. So I have the gradient of these two here. I have the gradient of PQ and QR. Now, that's saying something about the gradients of the corners I know. I know the gradient between 2 corners I know there, the gradient between 2 corners I know there. Let's now say something about the gradient here between 2 corners involving a corner I don't know, and the same thing down here. So if I want to write down the gradient of PS, this one here to start with, then S has got coordinates x, y, which I don't know. So let's find the gradient of this here. I've done the difference in the y's, the difference in the x's. And I know that the gradient of RS is similarly done, the difference in the y coordinates, the difference in the x coordinates. Now, here I've got links between numbers and algebra. Okay, looking at my diagram, I can see that QR and PS are parallel. They have the same gradient. So I can set my numerical value for QR of 3 equal to my algebraic version of the gradient PS. So setting those equal gives me this thing here. I'm never going to be able to solve this to find x and y because it's only one statement. One equation can't find 2 unknowns. But I multiply through and tidy it up, and I get that 3x minus y is 15. I'm now going to say that PQ and RS are parallel, so they have the same gradient. PQ is a gradient I know is -1. RS is a gradient I know in terms of algebra, so I set those equal, and that gives me a second equation when I rearrange, that x plus y is 5. I can solve these because they're linear equations, simultaneous equations, 2 unknowns. Going through that, I get that S is 5, 0. If you felt a bit unsure about this in the exam, a bit insecure, I would suggest maybe as a wee cheat, you could draw your own little rough grid and basically check that this looks vaguely like a parallelogram. It's a good question because the parallelogram is kind of off-center. It's not kind of sitting all straight like this one here. I mean, this would be a very nice question if the Q and the R shared their y-coordinate, if they were at the same height, and if P and S shared their y-coordinate, that would be nice. Unfortunately, it's not that. So, let's go down, let's try another question here. This is another kind of treat question. It says, find the gradient of the straight line joining 2 points. All you do is have to just be consistent. The complication with this is all the negatives, so we'll take a step back here and do this in a bit of detail. So, gradient of AB, I'm going to do B take away A consistently. So the y-coordinate of B, take away the y-coordinate of A, I get this thing here. I'm then going to do the x-coordinate of B, take away the x-coordinate of A, I get this thing here. Being very careful how my minuses work out, I get 2 over 12, my answer is 1 over 6. Next example, it says, determine whether these 3 points lie in the same straight line. This links into an idea that you would have met in connection with the vectors at GCSE, showing that 3 points are collinear. That means lying on the same line. So let's just think about that for a second. So if I give you those 2 points there and connect them up with the same gradient, and I give you those 2 points there and connect them up with a certain gradient, then it wouldn't be enough to say these all lie in the same straight line if that gradient was the same as that one. They have the same kind of slope, but they're disjointed in space. Equally, it's not enough to say, well, hang on, here is a connection between 2 points, here's a connection between 2 points, and they share a point in common. So they must lie in the same straight line. That's not true either. To show that 3 points are on the same straight line, it must be the case that they have the same gradient. So the gradient between 2 points is the same as the gradient between two other points, and they have a point in common. They have the same slope, and they're tied together with a point. So let's look at that in action. So I'm going to find the gradient of AB, and I get 2/3. I'm going to find the gradient of BC, and I get 2/3. So this is promising. This means that AB and BC have the same gradient, but at this point it might be this instance here. They might be completely disjointed. But in this case it's quite obvious, because I'm even told by the nature of the question that B is a point in common. So A, B and C are collinear, or lie on the same straight line, because they've got the same slope, so they're not going to bend halfway through, and because they have a point in common. There's nothing special about going AB and then BC. You could have, if you wanted to, investigated AC and then, for instance, AB. If they've got the same gradient, that's nice. They've got the potential to overlap completely, and they would have A in common, so they would all lie on the same straight line. Okay, so this is quite a classic and quite a straightforward question. The only complication in this is the kind of presentation of how they're giving you the line, and the temptation to make a very classic mistake here. So it says find the equation of a line parallel to this. Okay, so I'm trying to find out lots of stuff about this parallel line. So in this question, I'm going to start by saying that the parallel line is y equals mx plus c. Any straight lines y equals mx plus c. And as the question progresses, I'm going to find all the unknown things. I'm going to find m and I'm going to find c. First thing I'm going to try and find is m. So if these lines are parallel, they have the same gradient. So I would like to know the gradient of this thing here. And here's where there's the temptation to go wrong. People automatically say that the gradient of the line is the number in front of x. That's true when it's written in the correct form. The gradient of the line is m when you write it in the format y equals mx plus c. If you don't have y sitting by itself and positive, and this presented like this, you can't just lift out the number in front of x. So the gradient of this line is not 3. I have to rearrange this back into the form y equals mx plus c. So that's what I've done here. I've brought the 3x across, become minus 3x. I've divided through by 4, and I can see that actually the gradient of this line is actually minus 3/4. So a parallel line would have exactly the same gradient. So at this point here, I've written down that my parallel line is y equals minus 3/4 x plus c. Now, to find c, I need to use a point, and I've been given a point. I've been given minus 1, 1. So if I plug x is 1 into this, and y is minus 1 into this, my c value can be found. So working through that, I get c as 1/4. So my answer is y equals minus 3/4 x plus 1/4. You were asked to twist it back into this format here. So what I've done is I've times through by 4 to get this thing here, and I've brought my x term and my number across to get this expression here. What's really quite important here is they would have to say in the exam here where a, b and c are integers. Otherwise, you could leave all kinds of crazy answers here. You could have written 3/7 x, 4/7 y, minus a seventh equals 0. That's exactly the same equation. The purpose of tidying it up like this format here is to have whole numbers. If they didn't say that, I think it would be fair to assume that when you see that there, a, b and c should be whole numbers. If you've got one awkward fraction left, just times through by the denominator to make sure everything is a whole number. So next example is this one here. I don't know why that red bit's staying up there, but hopefully it won't interfere too much. So, find the equation of the line perpendicular to this one here that passes through 3, 1. Give your answer in this form here, and again we're going to assume that a, b and c should be integers, should be whole numbers. The only slight difference this time is it says perpendicular. So first of all, let's extract the gradient of this line here. Okay, so rearranging this line to get y completely by itself, I get this thing here. So the gradient of this line is 3/2. So a perpendicular line would have a gradient of the negative reciprocal of 3/2. So you make it minus and you flip it, so my perpendicular line has a gradient of minus 2/3. So here's my sort of journey from my unknown perpendicular just being a straight line, y equals mx plus c. I now know what m is, so that's plugged in. M was found by finding the negative reciprocal of this line's gradient. I've got this point here, plug in the coordinate I know, that allows me to find c. Writing it like this is a perfectly valid answer. At this point you have found the perpendicular, you just haven't yet given it the correct form, which would lose you a mark. So here, the only really complicating thing here, stopping it being nice whole numbers, is this fraction here. So times the whole thing by 3, and you get this here. Bring it all across to get a 0 on one side, and you have 2x plus 3y minus 9 equals 0. Here's a very generous and quick question to finish with. I can get this done under a minute. So let's see. The line y equals x plus b, you know nothing at all about it. A is the gradient here, normally called m. B is the y-intercept, normally called c, is parallel to this line here and passes through a certain point. Well, if this is parallel to this one here, then the gradients must be the same. So straight away I know that a is 2. How am I going to find out what b is? Well, if I already know that y equals 2x plus b, because a has been found, then I'm going to plug this point in, give me 7 equals 2 dots and minus 1 plus b, rearranging gives me that b equals 9. You don't necessarily write this out again with these values plugged in. It didn't say write out the equations line, it said find the values of a and b, and those are my answers.